Okay, everyone, so let's have a little short process about with momentum, its conservation and forces, and like some key terms, definitions of things that we need to be sort of clear on and aware of. So the first thing is let's define what we mean by momentum. Okay, so momentum. Momentum, which is actually often, in this case, it's a thing called linear, because it's momentum going in a different line, is equal to the mass times the velocity of an object. So we've got a unit of kilogram meters per second, because that's in kilograms, and that's in meters per second. So the momentum of a singular object is just the mass times the velocity. The main thing that we deal with that is the conservation of momentum. Okay, which is a law which states that when two or more objects interact, the total momentum of the system is conserved. However, there's always an important qualifier: unless an external force is acting. Okay, so if you look at something and the momentum is not, the momentum doesn't appear to be conserved, it means that there's an external force to the system that's acting. Now, if you then take another step back, and you incorporate whatever's causing that force into your system, then yes, the momentum will actually still be conserved. It's still, so whether you're dealing with it on the level of just a simple collision, or you're dealing with it at the level of of galaxies interacting, that is something that will be true. But generally, we use this for collisions. Okay, so this is useful in collisions. Of collisions. Okay, and we can do that as a little example. Okay, so we can say, okay, let's have an object A and an object B. So let's have object A have a mass of 0.40 kilograms, and let's say it is got a velocity of 1.2 meters per second, and let's say it's moving that way. And let's say we've got object B. We'll make object B a bit smaller, and we'll say that object B is moving that way. So it's got a mass of 0.1 kilograms, and let's say it's got a velocity of 0.2 meters per second moving to the left. So what we do is we say, okay, let's work out and let's say afterwards, let's say they stick together and they're moving off, and we want to know what is the velocity afterwards. What is the velocity of this thing afterwards? So what we have to do is add up the momentum of A and the momentum of B, and then that would be the total momentum of this sample here. So we can say the momentum, which is a symbol of P, is equal to 0.4 times 1.2. So we've got 0.48 kilogram meters per second, and 0.1 times 0.2, so we've got this one. However, it's going the other way, so this would have a negative velocity to show it's moving in opposite direction. So we have a negative momentum of 0.02 kilogram meters per second. So that means our total momentum to start with is equal to 0.48 plus minus 0.02, so that equals 0.46 kilogram meters per second. So we've got a total initial momentum which is slightly smaller because obviously got this one which we're saying is going to flip that way and it's positive. We've got the other one moving the other direction, so it's negative. So what that means on this side, well, what do we know? Well, we know the momentum is equal to 0.46 kilogram meters per second. We know the mass because that's just now this plus this. So we've got 0.5 kilograms. And so we want to know the velocity. And we can use momentum equals mass times velocity. Velocity equals momentum over mass. So we get 0.46 over 0.5, which comes out as being 0.92. And that's going to be plus because we've got a positive momentum. So that is 0.92 meters per second. And that's our answer to that one. So that's how we can use the conservation momentum in a collision. And it doesn't really matter if they make it more complex. They could have these two objects not stick together. Various different things could occur. But essentially, you just treat them all individually. It's very similar to solving a moments problem where there's multiple moments. You just add them all together on one side, and then that total must equal all the ones on the other side added up. So even if these two objects didn't stick together, it just adds another step to the problem of working out the momentum of each one individually. So that's what we mean by the conservation momentum, and the outcome is almost always about working out the velocity of an object after the collision by being told what happens. Collisions come in two types. So there are two types of collision. There are elastic collisions, which is where the kinetic energy and the momentum are conserved. And then we have another type of collision which is called an inelastic collision, which is where kinetic energy is not conserved. But because total energy always must be, that just means that energy lost via sound, heat, so on. But momentum is conserved. So sometimes if you're told that there's an inelastic collision that can sometimes enable you quite easily to get velocity a different way, or to work something out. So sometimes look out for if they tell you it's an elastic collision, because it means that there's another way of working something out. So it may be that you don't immediately think, hang on, how am I solving this problem? If you're told something's elastic, it means you know there's something else you know, there'll be another value that you know. So those are the two sort of defining types that are important to know. And yeah, that's generally the thing with collisions. So we're going to do a little bit of an Isaac physics series of problems that look at collisions and look at solving them, and get happy with all those things. But hopefully that's a good summary.